This video, we're going to show how we can use dynamic programming to improve the performance of the partition problem that we just solved in the previous video. So in the previous video, we wrote this partition helper function to help us with our can partition function. And what you'll notice in the picture on the far left bottom is that we use the principle of mathematical induction. So if we take the top domino that has arrows going leftwards in red or rightwards in blue, we can see that in our code in line 54, our bigger problem that we're working on is being helped to being solved by these two smaller problems, partition helper right here in line 54, or the other partition helper call, which is also in line 54. And those kind of represent the two dominoes that you see with the arrows coming out of them into our problem. So they're essentially, we're choosing which one of these two leads to a better solution. So these two recursive calls are leading to a solution, so to our bigger problem. And I'm trying to represent that with a left arrow and a right arrow, so the red and blue arrows. So that was the idea of using mathematical induction to solve our problem recursively. So one of the issues that we have is that this is like the kind of recursive call tree that we get with our problem. And so what you see is that we have the array, and then we have our target value, and we get these recursive calls. So in the first case, when we were deciding whether to take the last 5 in the top array in the picture on the bottom left, we had to decide whether to take it or not. And so if we took it, our target value went to 6 instead of 11. And if we decided not to take it, our target value stayed at 11. So what you'll see is that at the bottom, you'll see two underlined calls. And in the two calls, what you'll see is that they're the same exact call. And usually in other problems, you tend to have more calls that are exactly the same. It's when you have two parameters like you do here, there might seem to be fewer calls on smaller problems, but if you make a bigger problem, they do tend to show up. So the question is, like, how do we minimize these recursive calls? And the natural way of thinking about this is like, hey, what if I just like saved these calls and used those calls to look up that value? And that technique is called memoization. And memoization, what's nice about it is that it's easier to understand and read than dynamic programming. But in this case, it's a little harder to implement because the memoizations, like, you would have to have a way of describing the first argument of the array that is unique. So I'm not going to go into too much detail on that, and we're going to use dynamic programming because it's a little easier to implement. But it's a little bit harder to understand. So we're going to go through that right now. So in a dynamic programming, if we're going to make this into a dynamic programming problem, what we do is we're going to start, instead of starting from the end of our problem, we're going to start with the smallest problem that we actually have and go from there. So if you look at this picture, we have this table. And in this table, the target value is represented on the left axis, and the array value, the contents of the array is represented on the top axis. And what you'll see is that in our problem, what our initial problem is represented in this grid as this bottom right corner. So this is when we have all the elements, and the target value is 11. So what we're going to have to do is we're going to have to return this value at the bottom when target value is 11 and we have all the elements. But to do that, we're going to have to fill out this table And what's going to happen is this table is going to move from the top left corner, and it's going to slowly move right, and then it's going to slowly move down until we hit this bottom right corner. And so it's kind of like dominoes falling, and we'll try to understand how to think about that. So, okay, so one of the things that you'll note is that this problem actually corresponds exactly, like it might be like, oh, we have to start over again new, but it actually corresponds a lot with we've already done a lot of the work with our cross product of type comments table that we have at the bottom right. And so we can use that. So if you see, like, for example, where it says out of the array, which is like this case in the picture, it's when at the top where you have this empty array. And you can see that when we're out of the array and the target is 0, which is right here, that all of these values should be true. So this top row should be all true. And then likewise, we can see that when we're out of the array and the target value is greater than 0, all of these values from target value 1 in this empty array column to 11 should be false. So if we fill that out, what we'll get is this table right now. So you'll see we have true at the top and then false all the way down. And so using this information, we fill out the table. So let me kind of explain how to see things with like box 4 in our type comment thing. Remember how that's the meat of the problem. That's sort of like the tricky part. And so our problem in the picture, again, is represented by the star in the table where the row is 11, and we have all the elements of the array. And so just like in our partition helper, we could choose to take the 5 or not the 5. And we want the best answer. So if we choose the 5, what's going to happen is that our target value is going to go down to 6. And we're going to have one less element in the array. So we're going to be at this top box, this kind of slightly colored box right here. And that's going to be our first argument. It's going to be the equivalent in line 54 of that first recursive call. And then the second recursive call is going to be equivalent to this box right here at the bottom, where if we didn't take the 5, we're left with a target value still of 11 and with one less item in the array. And so that's kind of how you know where you need to look in the table. But of course we need to have, what's clear from this is that we have to have these two previous answers before we can solve our problem in star. So we have to have these colored boxes solved before we can do find our star answer. Because this is we're not going to solve it in a recursive way. So we're going to go from what is called a top-down approach. And so I'm not going to go step through writing the code with you line by line in the partition problem dynamic programming portion, but I'm going to walk through it and talk about it. So here's the dynamic programming version of the code. And so one of the things that I added that our other function could get away with because of the way it was written was that I made sure that the target value is an integer. Right here, it's not an integer. Right here, it didn't, before in can partition, it didn't have to be an integer. But in this function, we made sure that it's done beforehand, because in the previous function that we wrote, partition helper kind of dealt with issues with non-integers. And so we make sure that we send only integers as the target. And we see that in line 35 that I added, I kind of type coerce target into being an int if for some reason it's a float. Well, it is a float because total divided by 2 is a float. And you could also, I could have also done that slightly differently. There's different ways you could do that, but that's just the way I implemented it. And so if we go to our partition helper with our dynamic programming problem, So what you have to do is you have to make a table, and in each language it's slightly different. And in Python, I used uh, I used uh, I used these four in methods to make a two-dimensional table where the rows are the target value and the columns are the uh, the 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 state of our array. And so as you can see in line 50, what I'm doing, I'm going off this type product cross product of type comments table, and when j is in range, I'm making sure that when the array is empty, essentially, I'm making sure it's always returns true. So I'm filling in true in this first row, and then you're seeing in line 53, I'm putting false for the first column after 0 and empty array has been filled. And so now it's about filling in our table. And so this code kind of is very similar to the code in a way of our previous code, but it's a little trickier to see because it's harder because we use I, J, and the indexing is kind of different. And I sometimes actually have trouble with writing the DP version of the problem, and that's because like it's easy to get the indexes kind of confused and mixed up. And like for instance, like I in this case is your current value of your target, and it's not the same way we used target in the previous problem. In the previous version, we used target as a changing value. Here, target is a fixed value, and we're iterating to target. So I is effectively our target. And as you can see in the code, we do something very similar to the code in the previous video, where I minus the array. We make sure that if we take the item, for instance, if we took the common example that I've been using is that when the target is 6 and the current element that you're looking at is 11, and if you take it, then the target becomes -5, and that's not possible. So this is what's taking care of that. And then this else statement is filling in the DP table in the same way that we talked about previously about box 4. And so what's going to happen is our table is going to fill out, going from left to right and then slowly down. And eventually we're going to be able to solve our problem at star in the picture. And that's going to be, that star is going to be solved by being either knocked down by the domino at 6 in one of those two colored boxes. And that'll knock down our answer, and that will give us our solution. So so I just return DP target, which in our case is 11, and the length of the array. So that's this box right here. And so if we run our test cases, one of the things I did in the test cases, I slightly changed one of the tests because in test partition helper, I had this case where 8.5 was coming in as a target. So we'll go from here. Okay, so it shows that both of our tests pass. So I would say that one of the things that I didn't mention in the video and I didn't do very well is that I should have spent more time building a little bit more tests, and I should have used this type comments you could use the type comments to inform you on what you should test. So like for example, if we look at the cross product of type comments at the bottom, what you'll see is that each box is true. There's a true box, a false box, a true box, and another box. Well, what I should make sure is I should test each one of these cases, or like pick a point or pick an example that satisfies all of these 4 cases. And that's a good way of thinking about testing, and that's a good way of using your model or your map to give you a better idea of what to do in your actual problem. In the next video, we're going to talk about the runtime of the dynamic programming problem version of this can't talk right now properly. So let's try that, and I'll see you in the next video.